Hello and welcome. Today we're diving into a topic that's literally all around us, air quality. It's so important for our health, for the planet, and yeah, it's a huge part of your O-level chemistry syllabus. So let's get right into it. You've definitely seen this before, right? That haze that sometimes just settles over our city, making everything look kind of blurry. We know it's air pollution, but what is it really? Like, what are those invisible chemicals that make it so bad for us? Well, today, we're going to use chemistry to pull back the curtain and find out. So, here's our game plan. We've got 5 main stops. First, we'll figure out what's in clean air to begin with. Then, we'll meet the invisible intruders, the pollutants. We'll see the damage they cause, but also, and this is the cool part, how chemistry actually helps us fight back. Finally, we'll zoom out to the biggest challenge of all, our warming world. Let's do this.
Right. Section 1. Before we can even talk about pollution, we have to know what we're starting from. What are we actually breathing in every single moment of every day?
So, it turns out that clean air isn't just one thing. It's actually a mix of different gases. The main one, taking up a huge 78%, is nitrogen. Then you have oxygen, the stuff we need to live, at about 21%. And that tiny little slice left over, that 1%, that's a cocktail of other things, mostly argon with a little bit of carbon dioxide.
So that massive 78% is nitrogen. It's everywhere, but here's the key thing from a chemistry point of view. It's super unreactive. Why? Well, in a nitrogen molecule, you've got 2 nitrogen atoms locked together by an incredibly strong triple bond. It takes a ton of energy to break that bond, which is why it just kind of hangs out in the air and doesn't bother us.
And you know what? This links back to a core concept you've probably already covered. Because each of these gases has its own unique boiling point, we can separate them using fractional distillation. We just cool the air way down till it's a liquid, then slowly warm it back up. Each gas boils off at a different temperature. It's the exact same principle we use to separate crude oil. Okay, so we know what clean air is supposed to look like. Now let's meet the villains of our story, the air pollutants. These are the chemicals that sneak into the air where they just don't belong. Our first pollutant is sulfur dioxide, or SO2. You'd know it if you smelled it. It has this sharp, choking odor. Now, it does come from natural sources, like volcanoes erupting, but the main problem for us is when we burn fossil fuels in power plants and factories. That's the source you really need to remember. Next up is a really dangerous one, carbon monoxide, or CO. It's colorless, it's odorless, and it's made when fuels don't burn completely, like in a car that isn't running properly. And here's why it's so deadly. It sticks to the hemoglobin in your red blood cells, permanently. Once it grabs on, that cell can't carry oxygen anymore. It's a true silent poison. So, we've met the pollutants. Now let's look at the fallout. What kind of damage do these chemicals actually do when they're out in the world? Well, when pollutants like sulfur dioxide and nitrogen oxides get into the atmosphere, they dissolve in the tiny water droplets in clouds, and what you get is acid rain. Now, normal rain is already a little bit acidic, but acid rain can be up to 30 times worse. It messes up the pH of lakes and soil, which is devastating for fish and for entire forests.
Now let's travel way up, about 15 to 30 kilometers above the ground, into a layer of the atmosphere called the stratosphere. This is where we find the ozone layer. Think of it like the Earth's natural sunscreen. It's a shield of O3 molecules that blocks most of the sun's dangerous ultraviolet, or UV, radiation.
But this protective shield came under serious attack. Just look at these images. They show the ozone hole over Antarctica. Look at the difference between 1980 and 2020. That dark blue area, which means there's very little ozone, just exploded in size. So what caused this?
The bad guys here were a group of chemicals called chlorofluorocarbons, or CFCs for short. They used to be in everything from aerosol cans to refrigerators. Here's the destructive chemistry. High-energy UV light zaps the CFC molecule and breaks off a chlorine atom. That one single chlorine atom then acts like a catalyst, starting a chain reaction that can destroy thousands upon thousands of ozone molecules. It's a total wrecking ball.
Okay, quick brain check to help this stick. Pause for a second. What was that 3-letter acronym for the chemicals that destroy the ozone layer? You got it?
It's CFCs, chlorofluorocarbons. Remembering that one is super important.
Now, I know this all sounds pretty gloomy, but don't worry. This is where the story takes a turn for the better, because the very same science that helps us understand the problem also gives us the tools to fix it. This is chemistry to the rescue.
Take this device. It's a catalytic converter. Inside your car's exhaust pipe, hot, dirty gases flow over this honeycomb structure that's coated with precious metals like platinum. These metals act as catalysts, speeding up reactions that turn harmful pollutants into harmless stuff. Toxic carbon monoxide becomes carbon dioxide. Harmful nitrogen oxides become harmless nitrogen gas. It's a perfect real-world example of redox reactions in action.
And what about the big power plants churning out all that sulfur dioxide? Well, we can actually scrub it clean using something called flue gas desulfurization. It's pretty straightforward. The dirty gas with all the SO2 goes into a chamber. Then we spray it with powdered limestone, which is just calcium carbonate. It's a classic acid-base reaction on an industrial scale. The acidic SO2 reacts with the basic limestone, and it forms a solid that we can just remove. Simple as that.
We've seen how we can fight specific pollutants, but now we need to zoom all the way out and look at the biggest challenge of all, the enhanced greenhouse effect, which you probably know as global warming. Here's the basic idea. Step 1. The sun's energy comes in and warms up the Earth. Step 2. The Earth radiates that heat back out towards space. But, and here's the critical step 3, certain gases, especially CO2, act like a blanket and trap some of that outgoing heat. A little bit of that blanket is good. It keeps our planet livable. But by burning fossil fuels, we're making the blanket thicker and trapping way too much heat.
So what does all this extra heat actually mean for us? The consequences are huge. We're talking about deserts getting bigger, more intense heat waves, and stronger storms. But a couple of big ones to think about are the oceans getting more acidic and, of course, the ice caps melting. When that ice melts, sea levels rise, and that's a direct threat to coastal cities all over the world, including Singapore.
And the main thing to realize is that this is all connected. This map helps tie it all together. See? We start with clean air. Then pollution introduces these bad chemicals. They cause immediate problems, like acid rain and ozone holes, but they also crank up the greenhouse effect, which leads to climate change and all its consequences. But look, the map also shows our solutions, like catalytic converters. It's all part of the same big story.
And this is really what I want you to take away from our explainer today. I know it can feel like a huge, overwhelming problem, but the solutions are found in the very science that you are learning about in your chemistry class. You're getting the tools not just to understand the problem, but to actually be part of building a better future.
So I'll leave you with this final thought. We've talked about huge industrial processes and global issues, but small actions really do add up. So now that you know the chemistry, from combustion to catalysts, what is one small change you could make in your own life to help? Just think about it. Thanks for tuning in.